Hello everyone, today we are going over buoyant forces. So I want to go over the quiz questions and I also want to go over the lecture examples. So let's start with just understanding the equation for buoyant forces. We can read off this quote from Archimedes' principle. The buoyant force is equal to the weight of the water displaced. Now if you recall in our previous videos, we've said that the weight force of an object, the force of weight, is equal to the mass of the object times the gravitational acceleration on the object. So if the buoyant force is equal to the weight of the water displaced, we can then say that the mass of the water displaced times the gravitational acceleration is equal to the buoyant force. And you can even extrapolate this further when considering the actual equation of buoyant force, which is the buoyant force is equal to the density of the liquid that the object is in. So this P-ish symbol, I don't know the Greek term, but it's P. The density of water, so it's specifically of the fluid you're in, times the volume of the object. So V of object, so this is of liquid, times the gravitational acceleration. And how did I get this equation here from this equation here? Well, we can kind of consider, let's switch out a couple variables. We can say that when an object is completely submerged, the volume of liquid displaced is equal to the volume of the object. So therefore, when we are writing out the buoyant force of an object, we can say that's equal to the mass of water displaced divided by the volume of water displaced. So this mass divided by volume is density, times the volume of the object times gravitational acceleration. So we said that the volume of the liquid displaced is equal to the volume of the object when the object is completely submerged. So therefore, we can cancel out these values and get this equation. So that's just one way of dimensionally analyzing this equation. This is the primary one you need to know. The buoyant force is equal to the density of the liquid times the volume of the object submerged times the gravitational acceleration. This specifically means when I say volume of the object submerged, this specifically refers to the amount that's underneath the surface of the water. So if you have a box that's half floating, half underneath the water, we are only considering the volume of the object underneath the surface of the water. So that top part isn't displacing any water, meaning that it does not impact the equation here. So with that knowledge, we can then finally begin question 1. Which of the following is not a property of the buoyant force on a fully submerged object? It is always upward. Well, this is true because if we were to draw a free body diagram of a box that is just about completely submerged, it's like with water level, we see that the weight force is acting down. And in order for this to stay at rest and not go anywhere, the buoyant force has to be upward. So F sub B and weight. So therefore, buoyant force has to be upward to counteract the weight force. So A is true. It's proportional to the mass of the object. Well, if we look at this equation here, nothing includes the mass of the object. The density part of this equation is referring to the mass of the water displaced. The volume is referring to the volume of the object, not necessarily the mass of the object. And then G is the gravitational acceleration. So the mass of the object is not considered, is not a property of buoyant force. So we'll keep a dot there. Might be right, might be wrong, but we'll continue. It's equal to the weight of the fluid displaced by the object. Well, if we come back up here, we said that the buoyant force is equal to the mass of the water displaced times the gravitational acceleration, and we derived it from this equation here by making a couple assumptions about what's going on, and we had ultimately said that the mass of the water displaced is equal to the buoyant force, or is integral to calculating the buoyant force. So, yes. And we also said that the weight force of the water displaced is equal to the buoyant force. It is proportional to the volume of the object. Well, in this equation here, we have volume of object intrinsically within the equation. So that means it must be important, meaning that D is false and B is the only correct answer. Continuing along here, there are 3 cubes of identical size. So already I'm thinking volume is equal, V equals V equals V, 1, 2, 3. One is made of lead and rests at the bottom of the pool. Another is made of aluminum and also rests at the bottom of the pool. The third is made of wood and floats half submerged at the surface of the pool. Which of the following correctly rank the buoyant forces on these cubes? So, we know that the volume of each of these objects is the same. The mass we know is not the same, but we also know from the equation of buoyant force that the mass of the object is irrelevant when considering the buoyant force of the object. So, let's draw a free body diagram for each of these. So I'm going to draw a mini pool. So this is our pool here. We have the wood box, half submerged. And imagine these are equal in size. And then we have the aluminum box. And then we have the lead box. Again, I'm not an artist, so let's just imagine these are the same size. And we know that the volume of each of these boxes is the same. However, the volume that is submerged of the wooden box, so as we said here, the wooden box is half submerged. So the volume underneath the water, the volume that's displacing the water, is half that of the aluminum box and the lead box, because the lead box and the aluminum box are completely submerged, meaning that the volume of water that they're displacing is the same. So these two are equal to one another. In contrast, the wooden box is half submerged, meaning that V1 is equal to 1/2. Oh, that is a big mistake. Not 1 over V, 1/2 V2. The volume of box 1 submerged is equal to 1/2 the volume of box 2 submerged, which is equal to, and then we know that V2 is equal to V3. So therefore, when we're calculating the buoyant force, if we look at the equation, buoyant force is equal to the density of the liquid times the volume submerged of the object times the gravitational acceleration. What is the factor that's changing in this equation between these 3 scenarios? It's the volume of the object submerged. So therefore, we know that the volume of the object submerged for box 2 and 3, the lead and aluminum box, is the same, which then must mean, because the gravitational acceleration is still the same and the density of the liquid is still the same, that the buoyant force of box 2, which is the aluminum box, is equal to the buoyant force of the lead box. So we can say F sub B sub A is equal to F sub B sub L. So the buoyant force of the aluminum box is equal to the buoyant force of the lead box. So then we can already start and see which of these options says the buoyant force of aluminum is equal to the buoyant force of the lead. And we see that B is false. We see that D is false. But A, C, and E are all still in the picture. Now, we had also said that the only factor of the buoyant force changing is the volume submerged. And since the volume of the wood box submerged is 1/2 that of the volume of the lead and aluminum boxes, that must mean that the buoyant force acting on the wood box is less. So F sub B sub W is less than F sub B sub A, which is equal to F sub B sub L. I know this is very easy to follow, but breaking this down, this means that the buoyant force on the wooden box is less than the buoyant force on the aluminum box, which is equal to the buoyant force on the lead box. And when we look at the options, we see that C is the correct answer. This next question is a bit tricky. It's specifically a bit tricky. It was for me when I did this one, because it was difficult to consider what the question was actually asking for. So let's read through it together and break it down. Blocks A, B, and C are all the same volume and are at rest. Their masses are shown in grams in the image here. The scales, so the scales here, measure the tensions in the strings connected to the blocks. Which is the correct order of the scale measurements? So this question, I wasn't sure what it was initially asking, but it's asking for which scale has the highest measure. So which one has the highest measure of weight, basically. So we see that the only big difference between these objects is the mass, that mass C is bigger than mass A and B. And let's draw the free body diagrams of each of these boxes. So we have box A here, and what are the forces acting on it? Well, we have the weight force acting downward, and we can say that that is equal to mass times gravitational acceleration. So we know that mass has to be in kilograms, so 0.04 times, we're just going to round off to 10 for simplicity, times 10 for the gravitational acceleration is 0.4 newtons. That's the weight force acting downward. And then we have an indescript amount of buoyant force, which we could calculate, but we're not given the volume, so it's irrelevant. So we'll just use it qualitatively. So the F sub B, and we have the tension on the string. So the tension force, F sub T. So this is box A. We have box B, which has the same mass, which must mean that the weight force is also equal to 0.4 newtons. And we have the buoyant force, F sub B, and the tension force, F sub T. Now, recognize immediately that since these have the same volume and the same mass, since the density of the liquid, they're in the same liquid, and the gravitational acceleration on both these boxes is the same, we can then realize that the buoyant force acting on both of these is the same because they're both at rest. So they're both at rest. They both have the same weight, right? And they're both the same volume. So let's rewrite out the buoyant force equation, which is the density of the liquid times the volume of the object submerged times the gravitational acceleration. For the buoyant force of box A is equal to the buoyant force of box B. And since these are underwater, this must mean that there is still a force acting on between the string and each of these boxes, which we can then say F sub T plus F sub B, because they're at rest, is equal to F sub W. So the tension force plus the buoyant force must be equal to the weight of the object because it's at rest, meaning that because the buoyant force is the same for both of these, and these both have the same weight force acting downward, that the tension of box A is equal to the force of tension on box B. So we can already eliminate any option that doesn't include the weight of the scale saying that A is equal to B. So we can say that C is gone, we can say that B is gone, and that E is gone. So we have A and B left. And now let's consider box C. So if we were to write out box C, the force of weight acting downward is equal to 0.5 newtons, because 0.05 kilograms times 10 for the 10 meters per second squared is equal to 0.5 newtons. Now let's consider the upward forces, the tension and the buoyant forces. Well, we know that the buoyant force, since it's the same volume as boxes A and B, that the buoyant force on box C is the same as the buoyant force on box A and B. So we can draw a little hash line for all of these. And if you remember geometry, this dashed line in the middle here means that they're equal. But let's consider the tension force. If we know that box C is at rest, but the buoyant force is not scaled up to accommodate the increased force acting downward, we then know that the only other force that's acting upward to cancel out this downward force of weight is the tension force. This means that the tension force on box C must be greater than the tension force on boxes A and B, which would then yield a higher value on the scale when it's being measured, which means that the scale for box C would show a higher measurement than the values for box A and B, which are equal, which then means that the force of that box C has the greatest force of tension out of these three boxes, which then means that it has the highest scale measurement, which means that B is the correct answer. Finally, we have lecture question 4-3D, and it is asking which floating block is most dense, block A, block B, block C, or some combination of the three. And let's consider a couple scenarios before we approach this question. Let's recall that the density of water is equal to 1 gram per milliliter, meaning that for every gram of water, there is a milliliter of water. Let's then consider what happens when the density of an object is greater than the density of water. So we have object D at the bottom here, and object D is submerged, which means that object D must have a density. So density of object D is greater than the density of water, which is why it's submerged. The weight force acting downward is greater than the buoyant force acting upward, meaning that the object D has submerged. Now let's consider an object that has a density equal to 1 gram per milliliter, and we'll say this is object E. So density of object E is equal to 1 gram per milliliter. Well, when submerged, or when placed in water, it will be once it's fully submerged, it will stay there, because the volume of water displaced is equal to the volume of the box, and the mass of water displaced is equal to the mass of the box, meaning that we can then make correlations about the volume displaced and the mass of the box, which would then help us determine the density of the box. So we can say that the higher the density, the more submerged it will become, meaning we can just make this a ratio of amount submerged to total volume. So we can then say that box A is approximately 75%, this is all qualitative, like eyeballing. We can say box B is about 33% submerged just by eyeballing it. And then box C looks like about 50% submerged. Using this data, we can then make an inference about the density of the object. As the density increases, the percentage submerged increases as well. So once once the density is greater than that of water, the liquid, the force of weight of the box will be greater than the buoyant force, which means that's why it sinks. And this is just letter E again. That's why it sinks to the bottom. So therefore, for all objects that are still floating, the percentage of which it is submerged directly correlates to its density, and since box A is most submerged, it must be the most dense. And that's the answer. Hopefully that makes sense. If you have any questions, leave them in the comments. I will do my best to answer them. And thank you so much for watching. Have a great day.